Hello everyone. In this presentation, I will be explaining the concept of a pseudo static RAM or a register cell. Before this, we had discussed the concept based upon the dynamic memory cells, wherein we have discussed the one transistor type of dynamic memory cell. Also, we discussed regarding the concept of three transistor type of dynamic memory cell, how to design them by making use of NMOS logic or CMOS logic depending upon the application. In all those concepts, we have studied that the data, whatever it is stored in the form of charge in the capacitor, will be stored or will be retained as it is unless and until there is a lapse of 1 millisecond of time duration. So, before that, you are concentrating on the concept of refresh operation, wherein it has to or the dynamic memory cell is demanding a periodic refresh operation to be done. The advantage of performing the refresh operation is I have to retain the data as it is while performing the read operation. So whatever the data is written in the capacitor in the form of a charge, it has to be read as it is during the performance of read operation. So in order to have the read operation to be done perfectly, that is 100% perfect, I have to concentrate upon the lapse of 1 millisecond of time duration. So it becomes a tedious job over there. So in order to avoid that, we are going for the concept of static memory cells. So in case of static memory cell, we will be discussing on the pseudo static memory cell. So in this case also we will be using both the concepts, that is NMOS design as well as CMOS design for a pseudo static memory or a register cell. So if you see this particular diagram, it is a pseudo-static memory cell circuit diagram in terms of NMOS design style. As you are seeing only the NMOS transistors in this particular circuit, it will be the NMOS design style for a pseudo-static memory cell. In terms of operation, if I want to explain, I will come back to this later, that is the stick diagram. So this is the circuit diagram for the pseudo static memory cell in NMOS, and this is the stick diagram for pseudo static memory cell in NMOS. So it is having three NMOS transistors, one to perform the write operation, another one to perform the read operation, and the third one to perform the refresh operation. So here this phi 2 is responsible for performing the refresh operation in case of static pseudo memory cell. So this is refresh, this is write operation, and this is for read operation. Okay. Apart from this, I am having two inverters. So first inverter I will call it as inverter 1, and the second inverter I will designate it as inverter 2. So two inverters are present over here. So in this particular case, if I just want to compare it with the dynamic memory cells, the static RAM needs to be designed to hold the data indefinitely. It can hold the data for an indefinite period of time. One way is to connect the two inverters, that is inverter 1 and inverter 2. I will call this as a two inverter stages with the feedback. So with the feedback, I am connecting two inverters over here. So if you see here, write and read is designated in terms of a clock signal phi 1, and refresh operation is designated with the clock signal of phi 2. So we have already studied the timing consideration initially in the memory unit, wherein we have discussed there will be two-phase clocking system used, that is phi 1 as well as phi 2 clock phases. So it will be mutually exclusive in nature. So phi 1 is the clock signal which is used in order to perform the write as well as the read operation, whereas phi 2 signal will be used in order to perform the refresh operation. So now how does it work? If you see this particular circuit diagram, I have marked it as both the output as well as output complement. So output means whatever the input I have applied, that will be obtained. So whatever the data you are having stored in the bus, it will be read as it is, or it can be read in the complemented version also. So depending upon our application, whether we want the same thing to be written or read, and whether we want the complement form of it to be read or written, depending upon that I can select the output signals. I can either select the output from the inverter 2, or I can select the output from the inverter 1. say now I am performing the write operation. So if I want to perform the write operation, I will be asserting this write.phi1 signal as equal to 1, so that this particular transistor is turned on. Suppose if the bus is carrying a signal of logical 1 state, this has turned on, so this will be behaving like a closed switch now, which is having a signal 1 over here, that is bus is having 1, so obviously it will be carried as 1 towards the switch 1 terminal, and since the switch is closed, 1 will appear towards the output side of the switch, and that 1 is fed as an input for the inverter 1. So you already know, if I am applying the input as 1 for the NOT gate, the output obtained will be equal to logical 0 state. I have applied the signal as equal to logical 1, and if I take the output from the inverter 1, it is going to yield me the output complement signal. So complement signal in the sense I had applied the signal as equal to logical 1 state, but I am not going to have the same over here. Instead of that, I am having the value as equal to logical 0 state. So the reverse of that is being obtained over the output cell. So now, if there is a presence of a capacitor, that particular value will get stored in the capacitor. So if I want the exact same value to be stored in the capacitor, to be returned to the capacitor, then I am using the output 0, which has to be cascaded with the second inverter, and that 0 is passed into the inverter 2 as the input, and the output obtained will be equal to logical 1 state. So here I will be obtaining the output exactly similar to what input I have applied. So the capacitor will be storing the charge in the form of a logical 1 state. So this is how I am going to perform the write operation. Next, I am going to perform the refresh operation. So for performing the refresh operation, I have to make sure that phi1 is turned off. That is, phi1 is made as equal to 0, because both phi1 and phi2 should be mutually exclusive in nature. So here phi2 is mainly responsible for performing the refresh operation. So now if I want to so if I want to perform the refresh operation, at every clock signal of phi 2, the stored bit is refreshed through the gated feedback path. So this is the feedback path which is present in the circuit. So the refresh operation will be performed through the phi 2 signal. So that is how the refreshing will be done, and stored bit is held. Whatever the bit is stored, whether it is equal to logical 1 state or it is equal to a logical 0 state, the bit will be held till the phi 2 of the clock occurs at a time less than the delay time of the stored bit. So again it is similar to that particular concept itself. In order to read the data, RD along with phi 1 is to be activated. So here I am having the write operation already performed. Once performed with the write operation, apply this WR.phi1 signal as equal to logical 0 state. Then perform the refresh operation by asserting the phi2 signal as equal to logical 1 state. After performing the refresh operation, assert the read.phi1 signal as equal to logical 1 state in order to perform the read operation. Make sure that you are not going to perform the read operation when this refresh operation is going on. After completion of the refresh operation itself, I have to perform the read operation, because it will be read in the form of an erroneous message which is not feasible according to the application. So now I have to make sure that I am having this as equal to logical 0 state. I am having this as equal to logical 0 state, and I am having this read dot phi 1 signal as equal to logical 1 state while I am performing the read operation. So now let us see what will be the changes which are going to occur. So now I am having a particular charge stored in the capacitor, so that the write operation is already performed. So now that charge has to be read back in this particular bus. So now if I am asserting the read signal as equal to 1, that is read dot phi 1 signal as equal to 1, obviously this transistor will be turned on. So from the output, the transistor, then back to the bus. So that particular value can be read back in the bus value. So one thing we have to make sure in this particular concept is that I have to perform the read and write operation in such a way that when write signal is asserted with the value of logical 1 state, this value is equal to logical 0. When this is 1, this value is equal to 0 state. So that is how WR, that is the write signal, as well as RD, read signal, must be mutually exclusive in nature. And you are not going to perform any kind of read operation when you are using the phi2 signal, that is refresh operation is going on, so that you are not going to read any sort of erroneous message in the bus. You have to allow for other bus lines to run through the cell in order to make the connection of this VDD or the ground terminal if you want. So pull up part, I can have any of the transistors, whether it is designed in terms of an NMOS logic or in case of a CMOS logic. Depending upon that, there should be some sort of transistors in the pull up part also. In between bus and ground terminal, whatever the connections you are seeing, it is responsible for performing the memory operation. So the cell should be non-volatile provided that phi2 signals are present. So this is how the working of the pseudo-static memory cell takes place. So now if I want to convert this into a stick diagram, say I want to convert this into a stick diagram, once again in terms of NMOS design style, which means that the polysilicon should cross N type of diffusion. So now we here in this particular case, I am assuming this as inverter 1 and the second inverter as inverter INV2. INV2. This is INV2. In this case, write, anyways I have written, so this write signal is taken first, then I am taking the inverter 1. So inverter 1 is nothing but this entire structure what you are seeing here. So this is the stick diagram for inverter 1. Then I am concentrating upon the refresh operation, which is nothing but phi 2. Then again it is cascaded with the inverter 2. So this particular stick diagram what you can see is nothing but inverter 2, and last it is the transistor read dot phi 1. So these are the four distinct types I want. So three in terms of write signal, read signal, as well as the refresh operation, and 2 in terms of inverter 1 as well as inverter 2. So I am concentrating here in terms of NMOS design rule or NMOS design style, which means that these two inverters will be NMOS inverters. NMOS inverters. So single NMOS inverter I will draw over here. So it will be having in the pull up part the depletion type of NMOSFET whose gate terminal is shorted with the drain terminal of depletion type of NMOSFET. This terminal will be applied to VDD, and the pull down I will be having a single NMOS enhancement transistor wherein I will be applying the input over here and I will be taking the output from this particular terminal. So this is a single NMOS inverter. Same thing, I have to repeat it once again in order to, so there is two NMOS inverter. So I should have two representations of NMOS inverter in case of the stick diagram, also in case of circuit diagram. So in this I will be having one more transistor connected to the ground terminal and take the output out of this. So this is the VDD terminal and this is the ground terminal, or sometimes VSS also you can take. This is the input and this is the output. So inside the circuit I will be having the connection something like this. So if you compare it with this particular diagram, so write 1, I am having write 1 transistor over here, so that diffusion terminal. So this diffusion terminal is connected to the inverting, that is the inverter 1 input terminal. So this diffusion terminal will be connected to the inverter 1 input terminal. So this will be inverter 1, this will be inverter 2. So for these three transistors along with these two inverters, I have drawn the stick diagram over here. Say you are going to refer this in order to draw the inverter 1 stick diagram, and this in order to draw the inverter 2 stick diagram. So how we are going to draw? Let us start to draw the stick diagram. So first and foremost thing is right dot phi 1. So all the vertical layers I am going to assume it in terms of a polysilicon layer for right signal, phi 2 signal, as well as for read dot phi 1 signal. So if you see here, all these three layers, vertical layers, are polysilicon layers. So I am having a polysilicon layer, and there must be a diffusion layer in order to form this right dot phi 1 transistor. So I have drawn a diffusion layer. This is going to form right dot phi 1 transistor. So this transistor is nothing but right dot phi 1 transistor. So where the remaining two terminals, that is the source as well as the drain terminal, should get connected to. One of the terminal, that is the diffusion layer, this will be the diffusion layer, right? In diffusion also it is nothing but an N type of diffusion layer, whereas this is a polysilicon layer. So polysilicon should cross the diffusion layer. So I have assumed the vertical layer as polysilicon. It has crossed the diffusion layer. So one end of the diffusion layer should get connected with the bus. So one end of the diffusion layer, I have connected it to the bus terminal. Since this is N type of diffusion, and for bus VDD and ground terminal I have used metal layer. So these two are distinct layers. So make use of a contact cut over here. Next, the another end of the diffusion layer should get connected to the inverter 1 input. So this is the inverter representation. So pull up will be the NMOS depletion type. So pull up will be the NMOS depletion type. So this is the depletion type of NMOS transistor. Pull down will be enhancement type. So pull down is an enhancement type. This entire layer will be the vertical layer will be the diffusion layer. So that's what I have taken. Entire vertical layer is an N type of diffusion layer. So this is inverter 1 stick diagram. So from the gate terminal I have shorted it to drain terminal, and if I want to represent in this, this is the gate terminal polysilicon, and this is the source terminal, whereas this terminal is the drain terminal. Here also, so this is the gate terminal, this is the drain terminal, this one is the source terminal. Source terminal has to get connected with VDD. That's what I have done. Source terminal connected to VDD. Gate and drain should get shorted. So gate and drain is shorted through polysilicon because gate terminal is a polysilicon layer, and drain terminal should get connected with the pull down part. So drain terminal connected to the pull down part of the transistor. So this is the polysilicon layer. So that particular polysilicon layer is the input which has to get connected with the diffusion layer of the right dot phi 1 transistor. So this is the diffusion layer of right dot phi 1 transistor. For that it has to get connected. So this is done. The output of the NMOS inverter, the output of the NMOS inverter should get connected with the input of the inverter 2. So my inverter 2 is appearing over here. Again the replica of this, just copy paste once again. So this is your NMOS inverter. Pull up is the depletion type of NMOSFET. Pull down is the enhancement type of NMOSFET. So output of inverter 1 should be applied to the input of inverter 2. So output will be taken through the drain terminal, connected to the input means to the polysilicon terminal, which means that I am connecting this terminal to this particular layer, that is the right dot phi 1 diffusion layer, whereas this output is connected to the input of the NMOS inverter. So for this I have drawn the stick diagram. So now we are done with these connections. So that is applied to the input. Next, coming to the phi 2 concept. Phi 2 I have assumed the vertical layer as a polysilicon layer. Then it has to form a transistor, which means that there should be a crossing of N type of diffusion across the polysilicon layer. So one end of the diffusion layer should get connected with the inverter input. This is the inverter 1 input. So this is the inverter 1 input. So one end of the transistor has got connection with the inverter 1 input. Another end should get connected with the read.51 signal. So I will be first drawing the read.51 signal now. So vertical layer I have, this is the read.51. So vertical layer I have chosen it to be read.51. So diffusion layer of this particular transistor. So I have extended the polysilicon a bit and I have crossed the diffusion layer, which means that this is the transistor formed for RD51. So one end of the diffusion layer should go and connect with the bus. So one end is connected with the bus. Another end if you see, it should get connected with the inverter 2 output, right? So another end of the diffusion layer should get connected with the inverter 2 output. So this is the inverter 2, this is the output of an inverter. So it has got connected with the inverter 2 output. So what happens, inverter 2 output in turn should get connected with the phi 2 signal, the diffusion part. So this is the phi 2 signal transistor. So inverter 2 output has got connection with that particular phi 2 transistor, another side of the diffusion terminal, and then it has to get connected with the input. This I have already explained. So it has got connected with the input of the inverter 1. So this is regarding the connection of or the circuit diagram as well as the stick diagram for the NMOS design style in order to design the pseudo static memory cell. Next, the same concept we will be discussing it in terms of CMOS design style. I am making use of both PMOS as well as the NMOS transistors. So here if you see, in the previous case it was only NMOS transistor for write signal, phi 2 signal as well as read signal, but now it is cascading, that is parallel combination of the PMOSFET as well as NMOSFET. So for all the NMOS transistor, you are supposed to draw a parallel connection of a P MOSFET. So three P MOSFETs are present over here, inverter 1 and inverter 2. Now it is in terms of CMOS design style, which means the pull up will be the P MOSFET and pull down will be the N MOSFET. So I am following the CMOS design rule. So I am having a transmission gate, 3 transmission gates, so which are having a parallel combination. So how I am going to make the parallel arrangement is, say I will consider one particular example, that is write.51 signal as well as write.51 complement signal. I will assume this as write.51 complement signal and this particular layer as write.51 signal. If you see in this case, write.51 and write.51 complement both are connected in parallel with each other. One of them is P MOSFET, that is write.51 complement signal is a P MOSFET. So P MOSFET should be drawn towards the pull-up part. Pull-up part, say this one vertical terminal, I have used it as a polysilicon layer in both the cases. Then write.51 is having NMOS. So NMOS we are already familiar. It will be reserved for the pull down part. So these two should be connected in parallel. We have seen in the dynamic shift register. So it will be connected by making use of a contact. So assume this as a contact along with the metal layer and then you are going to join both the leads. So this is one connection. Another is use a contact cut over here, use a metal layer, use a contact cut over the other end and make a metal connection like this. So this is the parallel connection. So that's what you can see I have done every way. So this kind of connection has to be repeated 2 more times. So in total it should be thrice. So this is one connection. If you see this particular part. write dot phi 1 as well as write dot phi 1 complement connected in parallel. So this is write dot phi 1 complement transistor, this is write dot phi 1 transistor, and I have made a parallel connection. Similarly, you have to make a parallel connection for the read dot phi 1 and read dot phi 1 complement signal. So from the circuit, read dot phi 1 complement as well as read dot phi 1. So the order I have chosen it like this. First it is in terms of complement. Write dot phi 1 complement, write dot phi 1, then phi 2 complement phi 2, then it is inverter 1, this is inverter 1. Next it is inverter 2, and the last part is regarding the read operation. So it is read dot phi 1 complement, and last it is read dot phi 1. So for this, how to draw the stick diagram? So all these write dot phi 1, write dot phi 1 complement, read dot phi 1, read dot phi 1 complement, phi 2 and phi 2 complement must be arranged like this part, and phi 2 complement and phi 2 as well as read dot phi 1 complement and read dot phi 1. If you see, the parallel connection has been made by following this particular rule. Now that write phi 1 or write phi 1 complement parallel connection, this portion, so one end of the parallel connection should go and connect with the bus. So one end I have extended it and connected to the bus. Either you can use a diffusion layer and you can connect it by making use of a contact cut, or directly you can use a metal layer over here without making use of any contact cut. Both are true. Another end of the parallel connection, if you see, it has to go to the phi 2 and phi 2 complement parallel connection. And if you see here, phi 2 complement and phi 2, this is the phi 2 complement and phi 2, that is the parallel combination. So this much, if you see this portion, it is nothing but adopting this particular style. So now if you see, one end of write dot phi 1 and write dot phi 1 complement connected in parallel has to get connected with the bus, that is nothing but this connection. Another one should get connected with phi 2 and phi 2 complement in parallel. So phi 2 and phi 2 complement in parallel, another end should get connected with that particular connection. So this is that connection. Understood? Then I am having an inverter 1 over next. So this is the inverter 1. So here it is CMOS design. So how you are following the inverter circuit diagram? Pull up will be a PMOS transistor, pull down will be an NMOS transistor, join the gate to gate connection, and you are applying the input to this. So this will be applied to the terminal of VDD, and this will be connected to the ground terminal. So this is VDD, and this one is the ground. Okay. Then in between the junction of PMOS and NMOS, we are taking the output. So this is one inverter. Similarly, I want another inverter also to be placed. So in case of a stick diagram, I am considering a vertical layer to be say polysilicon layer. So this is a vertical layer of polysilicon. Then I am having P type of diffusion. This is N type of diffusion layer, and the P type of diffusion will be connected to the VDD, that is nothing but a metal layer. So obviously here I am supposed to make use of a contact cut. Then I am having a metal layer used for the ground terminal. So just for the clarity, I will erase it. So you are having a polysilicon layer vertical, that is the gate structure in this manner. So VDD connection will be applied through the source terminal of P MOSFET. Next I am having a metal layer used for the ground connection. Okay. So from here, that is the drain terminal to drain terminal, you are using a contact as well as the metal layer like this, and you are going to connect it to the output. Whereas here this terminal will be applied to the ground layer by making use of a contact cut. Since it's a CMOS design style, you have to use an N-well contact as well as P-well contact by marking a cross mark over the VDD as well as the ground, that is called as supply rails. So one CMOS inverter will be drawn like this. So that is what we have drawn in this particular inverter 1. So inverter 1 input should be applied to the right.phi1 complement other end of the diffusion layer where you don't have the bus connection. So this is your right.phi1 complement and right.phi1. One end is connected to bus, the remaining end is this one. So from there connect it to the inverter 1 input. So polysilicon will be the input. So extend the polysilicon a bit and connect it as an input for the inverter 1. So that is done. The output of inverter 1 should be connected to the input of inverter 2. So this is inverter 2, this is the input of inverter 2, and this one is the output of inverter 2. Just connect them together. Since this is a polysilicon, this is a metal layer, use a contact cut. So inverter 2 is done. Then inverter 2 output has to get connected with phi2 complement signal or the read phi1 and read phi1 complement signal. So first we will complete the read phi1 and read phi1 complement signal. So this is the parallel connection, follow exact the same rule what you have used for write phi1 and write phi1 complement, and one end of the read phi1 and read phi1 complement connected in parallel should go to the bus. So one end I have considered it with the bus, another end should go to the inverter 2 output. So this is the another end, so this is the output of the inverter 2, so it has to get connected with that. Also it has to get connected with phi2 complement where it is not connected with right phi1 signal, that is right phi1 and right phi1 complement connected in parallel. So phi2, so this one will be, this side is connected to right phi1 and right phi1 complement, whereas this side is not connected to that right signal. So for that the connection has to go. So this is regarding drawing the stick diagram in the case of CMOS design style. So apart from that, here I have used a VDD as well as ground terminal also to draw the CMOS inverter. Similarly, in case of NMOS logic also I had used VDD and ground terminal in order to draw an NMOS inverter. So hope you understood the concept of pseudo static memory cell or pseudo static RAM. Along with that, the two different styles what we have used in order to draw the circuit, explain its operation as well as drawing the stick diagram in both NMOS as well as the CMOS design style. So thank you for listening.